All right. Today we are honored to be joined by Conor Titania?
Titania.
Oh, my Shakespeare's not that good.
Yes.
McBride, and they will be talking about Effing W.
Yes. Okay. So there are sort of several different things going on in this talk, and it's important to try and separate them apart. Um, there are some interesting, I hope, ideas about programming with effects and handlers in a setting where stuff evolves in the background. I'll say what I mean there. There's also some, as you can possibly guess from this slide full or screen full of code, um, uh, a lot of dirty trickery going on in the Haskell implementation of the ideas, which has nothing to do with the ideas and everything to do with Haskell. Which reminds me, next April on the 1st, I must get around to proposing language extension synonyms as a language extension. Because I just want to be able to say language, kitchen, sink. Right, and the example that I'm going to use is actually, now I come to think of it, not so well chosen, but it seemed like base camp to demonstrate this approach to programming on Hindley-Milner type checking, because the problem I'm addressing comes from a problem I experienced writing a gnarly type checker, actually many years ago, 20-something years ago, when I was implementing Epigram 1. And there were various aspects about it which made me miserable until one morning in the bath, I realized that I wasn't implementing a type checker. I was implementing an operating system which happened to be coroutining a bunch of processes which happened to be checking types. And the realization that I was writing an operating system, that there was coroutining going on, and there were various kinds of communication happening, both synchronous and asynchronous, told me that what I was doing, trying to write a conventional program which works by recursion over the syntax tree of the source code, that was just not going to cut it. And having realized that, I then did something extremely gnarly and unpleasant, but at least I knew what kind of gnarly and unpleasant it was going to have to be. And part of the problem is this. Well, let's just think about various things that are going on. It's certainly enough of this is going on in Hindley-Milner type checking for you to notice. If you think about the sorts of stuff that happen when you're doing type checking or type inference, the source code contains a variable. You need to know what's the type of that thing. And so you need to ask something that knows, something that's bookkeeping the types of the variables that are in scope. What's the type of this thing? And sometimes you do that by carrying around an explicit data structure called the context, which tells you the types of the things. But in general, what's required is just that you shout to the world, what's the type of this thing? Wake me up again when you've told me. So you can think of it as if you want to think of that as one of the kinds of effects that can happen, you just issue a request to the world. You say, here's my resumption, call me back with the answer to this question. That's exactly the kind of thing we do in effects and handlers programming all the time. And the lovely thing is that You don't necessarily have to be called back straight away. It's just, whenever you know the answer to this question, call me back. But also in the world of Hindley-Milner type checking and all sorts of other kinds of gnarlier type checking, there's a whole bunch of stuff going on. Like when you have a function application, well, that's going to cause you to have a constraint that the domain of the function type, well, first of all, you're going to want the function type to be a function type. And then you're going to want the domain of that function type to be the same as the argument type. So that's going to create a constraint. And that constraint has, might involve types with unification variables in them. Those unification variables might get solved. So solving unification variables creates a kind of a timeline, right? So let me, what color will time be? Time's going to be blue today. So what happens in this process as we work through time is that, we might, in the beginning there are no unification variables and none of them have been defined. And then we might realize, because somebody instantiates something polymorphic, that we might need something called alpha. And now that's more than there was before. There used to be nothing, now there's alpha. And then maybe a little bit later we need another thing, and that's called beta. And then maybe a little bit later we actually get a constraint that allows us to conclude that alpha is beta arrow beta, and so on and so forth. So then something tricky happens. Okay, right, so here's more stuff, right? We're inventing new unification variables. We're going to need a source of freshness. That's another kind of effect that we might encounter in the system, the kind of Britney Spears, hit me one more time effect to get a fresh identifier. I remember once the Guardian Prize crossword was themed on Britney Spears. And lots of middle-aged men were writing in saying, I had to get my daughter to help me do the crossword. I knocked it off in 10 minutes. But I got lucky. Right, so what happens maybe is that some process that is talking to this environment where this is happening is maybe interested in, it asks a question, some command, which is paired with a response. I should have moved this slightly further on. Oh, I should check. Where's the eraser? There was one a moment ago. Where did it end up?
It's behind the bottle.
Gotcha. Yes. Let me get the timeline right. Right. So, yes?
The reason it's useful to think of this as time at all is because the information, once it's in there, never kind of goes away.
Yes, exactly. We might invent new variables and we might find out how variables get defined, but information only ever increases. So perhaps here there is a process which has said, what's alpha? And got the response, I don't know. And then does something else, some command with some continuation. Or resumption is the word I want to use. And maybe, just maybe, this command is a bit tricky to satisfy at the time. So we're co-routinging, there's a whole bunch of other stuff going on. And sometime later on, we're ready to respond. We invoke the resumption at this point. What does the resumption think alpha is? I mean, the result of asking what's alpha that delivered some value that is stored in the closure of the resumption, that got picked up here. And as far as that closure, as far as the function that we are now running is concerned, the answer to that question is what it was when the process went to sleep. Right? You know, you've got a bunch of, I mean, just think about it, you're writing a do block in Haskell, and you've got a bunch of left arrows, and an earlier one gets you a value that's the result of a query of some sort to the world, some effectful process. And then later on, you issue another such thing, and that blocks creating a resumption. But the answers to all of the earlier stuff is in the closure of that resumption. And my point is that sometimes, by the time the resumption wakes up, the information that it's working on is out of date. It's out of date in a particularly pessimistic way, because it's working off the back of old answers that it's not questioning, that are not as informative as they could be. And correspondingly, while nothing happens that is wrong, things which ought to happen that are right don't happen because the resumption's overly pessimistic. And that was what was going on. I was tearing my hair out saying, why isn't this type checking? There's enough information for this to type check. You know, why isn't it figuring it out? And it's because it's living in the past. Do you know the plot of the movie Goodbye Lenin? I haven't seen it, but I do know the rough plot outline, which is that at some point in the 1970s, some East German child's mother has a nasty accident and goes into a coma and does not recover for like 15 years, by which time the Berlin Wall has come down, you know, the Deutsche Demokratische Republik no longer exists, and you know, the world has changed, allegedly for the better, but when they're interacting with their revived mother, she doesn't understand what's happened, and they have to kind of pretend that it's still the communist era in order to keep her you know, in reasonable spirits, or whatever it happens to be. So I call this technical problem the Goodbye Lenin problem, because the resumption wakes up and still thinks the DDR is a thing. And so that's the kind of issue that's happening here. And I was trying to think, what are we going to do about that? So I actually want to skip. Oh, need to be focus does not follow eyeballs. Isn't that amazing? So I want to do a kind of vibes-based, right? You know, this is the end of the program. A whole bunch of definitions have happened that you haven't seen yet, but let's get some vibes. You can see that I'm writing some code in kind of old-fashioned monadic style with operators that look a bit like bind but are not exactly bind, and I'm writing a function called infer, which takes a term and gives back something timey-wimey. And it's got 4 rules, like classic Hindley-Milner, and it doesn't matter yet exactly what's going on here, but you can see here, right? The term is a variable, and I say, oh, what's the type scheme of X? And I get back a type scheme, and then I say, oh, instantiate the type scheme, and that will give me a type. And that's what Hindley-Milner says you should do with the variable. I mean, so what I'm hoping you'll get from this is not a deep understanding of how this Haskell works. What I'm hoping you'll clock is how close it is to the traditional Hindley-Milner rules. Okay, what happens? This is lambda xb. I say, guess a type. Declare that X has that type. And we always guess a monotype for the arguments of functions. And in the scope of that, infer the type of the body. And then once we've got the type of the body, we're going to return S arrow t. Now, hold on a minute. Just think operationally. When we said guess this type S, we had no information from the body of the function as to what the type of the input had to be. We haven't even started doing that type inference process yet. And here I am saying return S arrow t after we've inferred the type of the body. Is this S bound here the same as this S, the same as this S? And no new bindings happening. It had better be. What could possibly be going on that I just say S? Right, that's the point here. Is this program is confusingly simple. Here's function application. Got a function, got an argument. I say, infer the type of the function. I say, infer the type of the argument. I say, okay, I want you to take the function type and split it into a source and a target. And okay, why am I not just doing that with pattern matching? That should make you suspicious. But let's say the split operation is splitting a function type into source and target. And I'm saying unify the argument type with the source type of the function, give back the target type of the function. Now, hang on a minute. That unification, apart from anything else, is going to involve some kind of constraint solving. And, you know, some stuff is going to happen, right? Here's the function. We infer the function type. Then we infer the argument type. And goodness knows what we learn about the function type indirectly while we're inferring the argument type. And yet here I am, you know, insisting that the function type is indeed a function type, same ft, and giving back the t I got back here before we did the unification as the type of the whole application. I mean, it looks a lot like the rules you might write down, but nothing that could possibly work operationally. I mean, it's just too naive, right? You know? And then finally, here's let. So we got a let bound variable, the thing it's defined to be, and then we've got a body. We say, oh, infer the type of D. That's gives us a type scheme. And then we say, declare X to have that type scheme and infer the type of the body. What could be more straightforward than that? Notice nobody's talking about, you know, the Hindley-Milner, this is the point where there's this sort of kind of brain fart of generalization that is trying to figure out what on earth is happening with that stuff. Okay, so what on earth is going on here, other than quite a lot under the surface? Otherwise, this couldn't possibly work. Right. Back to the beginning. Right. Okay, so first of all, some general purpose machinery which conforms entirely to my regular modus operandi. Yes. It's practically a signature on the artwork that there is an infix operator, a binary infix operator, which takes 3 arguments. That's me, right? And, so this is the thing which takes 2 index types S and T and an index I and says we want the function type at that particular index, source to target. But we're always going to read these things as I'm trying to build equipment to talk about indexed things as if they were just normal things. So to talk about indexed things, talking as little as possible about the indices. You can think of this as predicate implication. S and T are not just types, they're predicates that talk about the state of stuff, and what we're saying is whenever S holds, T holds. And then we've got this all operator which turns a predicate into a type, which says this thing always holds. And these two go together. This is a liberal type synonym. We want the type synonyms to be expanded before we check that everything's fully applied. Otherwise, everything gets horribly ugly. Likewise here, this is pairing, but for predicates. This says S and T both hold at the same index. And down here we have the corresponding existential quantifier that says this holds somewhere. What else do we have? We have this thing which is constant, which takes an unindexed thing and says we're going to make it an indexed thing by ignoring the index. So we're going to be living in a world where stuff is indexed, and that index is going to be time. And you should think of time as somewhere on this timeline. Except it's not really a continuous notion of time, because time is made up of discrete events which cause information to increase. Okay, so along comes time. And what's going to be, time is going to be made by sequences of progress. So if we've got source and target times, what do we have here? We have it's a SNOC list, but it's an indexed SNOC list that says we have a bunch of steps. I haven't told you what steps are. I will. A bunch of steps that fit together like dominoes, and they grow at the right-hand end. So a step is going to be one incident of finding out. So this is a data structure that tells us our history, with the most recent end of it on the right, is the most closely accessible. And then we are interested in things which are timed. Category theorists should at this point say pre-sheaf. But what's happening is I'm simply saying timed things are things which are preserved by progress. So that's to say, a timed thing which arrives at time S can be updated by the progress that happens between S and T to give some new version of the thing at time T. And if this looks like map, but for morphisms of something that are not just functions, that's exactly what's going on. This is functoriality, but with respect to progress rather than element type. All right. And in particular, there's a standard implementation of update. You can think of this as update, which just says, well, if we know how to do one step's worth of update, then we can iterate that to do the whole lesson's worth of updating. And in particular, I note, oh goodness me, this is so pretentious. I note that in particular, updates are updatable by concatenation. You know. And what else? There's a way of throwing away boring information. Lots of things are timed. Isn't this good? In particular, that if you've got two things which are, so things that weren't paying attention to time in the first place can be updated by doing nothing. If you've got two updatable things, you can update pairs of them in the obvious pointwise way. Okay, but so that's the basic machinery where, in particular, progress is an explicit data structure, and we are explicitly cranking through it. So no mystery. Things are about to take another turn because we're about to have not one but two isotopes of the same concept wrapped up differently in the Haskell type class system. Right, so in particular, step one is to say, take our source and target indexed data structure of progress and hide it as a relation, as a constraint. So this less than or equal to source target two-place relation is saying that, and with the method lesson, that is just an explicit lump of data that represents the progress, is just saying that somehow, if this holds, if S and T are sufficiently recognizable, we can infer what the lesson was by instance inference. And this is double-ended. You have to know both ends to know what this thing is. But then I do a dirty trick. It's not a dirty trick, actually. It's a very clean trick, and it's an Estonian trick, where instead of holding on to both objects and asking what the morphism is, you hold on to just one end, and you say, is there a thing which connects to this, and if so, where does it come from in this instance? So this constraint seg2t is indexed only by a target time, and it's a way of saying, how did I get here? Please tell me, how did I get here? That's seg. What was the segment of progress that got me here? And and it must have come from somewhere. So once we know, if we know how we got here, we must know by what means and where from. And now we have a way to search. Let's suppose that the context in which we're doing instance inference is full of these seg2s. Then we can try and search for evidence for the existence of a whole path from S to T by saying, well, we know where we want to end up. We know the time now. We want to know how we got here from then. If then is now, great. Otherwise, how on earth did we get here? And then can we figure out a path that gets us to where we got here from? So we're kind of reaching backwards to say, oh, how did we get here? We got here from there. How did we get there? We got there from somewhere else, and so on, back to where we're trying to find our way back to. So this is kind of like retrace the steps one at a time that got us here from there. And it's going to work, right? This is ridiculously dangerous looking recursive instance inference, which I have to switch on overlapping instances and all the undecidable stuff because it's just a crazy recursion. But if we are in the circumstances that history is linear and that we got here, you know, by a sequence of segments, then this is a kind of ludicrously expensive solution to an extremely straightforward join the dots problem. Right? Each of these are going to be our points. Each of these lines is going to be a seg2 constraint sitting in the context. And if we pick a start point, you know, and an end point, we will say, okay, I got here from here, so that's this segment. I got here from there, that's this segment. Compose them up. That, you know, this is what happened between these two times. The context is now telling us what the history is. Okay? So what I'm saying is that if we arrange for these seg2s to arrive in the instance inference context, we will be able to persuade GHC to figure out these time sequences of progress steps. At which point we have this fabulously weaponized, cryptified version of stuff, right? So V is some indexed thing, and T is the time now, as it were. And I'm saying I have a cryptic V at T if I have a future-proof V. So what this is saying is, for all U, if we can figure out how to get from T to U, we have a V at U as well. So these are the future-proof things. And these are what we want to trade in, because these are the things which magically figure out how to update themselves. And this is the kind of weaponizing device, which is cryptkey. If I've got some timed V, so remember timed was, if you tell me the updates, this V will update. And I'm turning V's into cryptic V's, which is to say, I take something which is a type where we know how to update it, and I'm going to turn it into a thing which updates automatically by saying, find the lesson that got us from then to now, and then do the update process. So that's to say, look at the instance context, figure out what the update was as a data structure, and then do the update process. So now are you beginning to see what on earth, what must have been happening in that program? Right? Back here. All of these things are not just data, they're cryptified data. So when this T happens here, this T, that's why I'm not pattern matching, because this split operation is building in cryptification and handing me stuff that looks like it's just data, but it's not just data, it's data that knows how to update itself. So when I bind this T here and I say ret now T there, some stuff has happened, and what I'm really saying is, give me this T updated by whatever happened between the binding site of this T and the use site. So that will incorporate whatever we learned by doing this unification without me lifting a finger or saying a word. Right, where did we get to? Okay, there's some other crap which I don't really want to talk about. For some reason, I decided I was going to represent universal quantification in type schemes with de Bruijn indices in a well-scoped way, because it would be embarrassing if I did not. And so there's a whole bunch of stuff with that. Okay, now we're back to the timey-wimey story. Okay, so I'm finally telling you what a step is. And you'll be shocked to learn that a step is a single substitution of a closed monotype, a type with 0 free universal variables. So monotype being substituted for an existential variable, that's a step. And even more ridiculously, life gets easier if you pretend it doesn't actually make any change to the time. Because the point is not that actual times exist. The point is that hypothetical times exist. I'll get there in a minute. Then what are types? They are either existential type variables, universal type variables, or they are arrows. And in particular, closed types have no universal variables. So this number is how many universal variables are free. And then somewhere or other, we've got type schemes. Yes, so what happens here? So here I'm saying, well, this is what a time with a y is. It's a type indexed by a time. It's a world of dreadful portmanteaus. And indexing is purely phantom. It's a closed type. Okay, what else is important? Very little. Okay, one thing that's important here is that this sort of truly ghastly business of saying, oh, take this time index type, unwrap it, pattern match it as a function type, and then cryptify the pieces, rewrapping. And then all of that turns up into a pattern synonym, and this is the thing that I was using in the program to match against types, and all of the cryptification is being hidden in that pattern synonym. It's, you know, this is we are now watching synchronized swimming from below. Yes.
Why doesn't the pattern return a crypt type?
Think about it the other way around. Someone is going to hand us an actual concrete piece of data, and that's going to be the return type of the pattern. Yeah. So what's important is that the input types are crypt key, yeah, because we're pattern matching.
But won't we always be working on crypt types?
If we want to use this thing on the left-hand side of a program, yeah, then we can't directly pattern match on a crypt key thing. At least we can say, what's this now? And then we get an actual concrete type thing out. So it's the backwards thing. But then you can see I immediately wrap it up and say, what are these? What's this arrow thing? Okay, here's crucially, you know, guess what? One of the things you can update by a sequence of substitutions is a substitution. So this is the thing which says, like, you know, if we used to be substituting R for X and a whole bunch of substitution happens, then maybe we should consider updating R. Okay, no, this is the thing that says, how we update types. This says just do the substitutions to the type. This is the update thing. That says this is what in practice happens, right? We learn this thing, and now everything involving alpha gets updated. So this is the key thing that says types, as we know them, respect the passage of time by the action of substitution. But it is also the case that substitutions themselves can be updated. And substitution is just the thing you thought it was. Polymorphic type schemes, not terribly exciting. Dependencies, not terribly exciting. Yes, type schemes also have a substitution action. This is not super exciting. Oh, this is the trouble. I don't want to tell the story in that order. I want to move on to this thing, because that's just low-level gadgetry that will show up as part of the picture later. And let's not do it bottom up. Let's find stuff when we need it. Okay, so this is I think of it as the kind of unweaponized, fully explicit notion of a free monad for timed stuff. Right. Okay, here's the thing. You should think of so this type is Haskell's type. So you should think of a time arrow type as a condition. Think of it like an OR logic, right? Precondition, postcondition. So we're going to build the appropriate notion of free monad for these things, and what the commands are, the constructors of the free monad, are going to be predicate transformers, which tell us how a given target condition, or that a given target condition, can be achieved. So that's to say, these commands are commands which achieve a postcondition. That's how you should think of C. Says, that given a postcondition, which commands achieve it, starting at the current time. Then what is this V? V for value that we're trying to achieve. This is the postcondition for the whole process. And then this S is the start time for the whole process. So we're saying we've got a bunch of commands which we can make, each of which achieves some particular kind of postcondition. We've got a postcondition for the whole process. We've got a start time. When can we do it? Okay? So there's this thing called ret now, which says if our postcondition already holds, hooray, we can do it. So that's just the same thing. You want to return a value already? Great. All we've done is make that timed. So that's to say, you got a value now, return it. Okay? And then this thing says, we're going to call a command. So what happens? We got a command which achieves a result, and it's available at start time now, right? The process, read from the return type. We're starting at time S. We're ultimately trying to achieve V. We have commands from C available. So we pick a command from C that's available at time S, where we are now, and that has postcondition R. And that should be something we can do now. And then how do we carry on from there? Well, folks, we're going to, so this all is abstracting over the time at which the first command finishes. So what we're saying is, there will be some progress from S to our intermediate time. And we will actually, by then, have got ourselves an R. The postcondition of the command will be satisfied. So we're saying, whenever in the future, we know how we got there from S, and we've actually achieved R, then we have a plan that will carry on our merry way to achieve V. So what we're saying here is, we have to be ready to carry on after C at some later time that we don't know, and still have the rest of the plan to reach V. So here, the resumption is giving away to the environment the option to make time pass. We don't know when we're going to be woken up with our result in type R, and we have to be ready whenever that is to carry on to deliver V. But the good news is we are at least going to be told what the hell happened between the time now and whatever time we get woken up. So we're going to have the information we need to catch up with what happened while we were asleep. Okay? What happens? Yes, we have to show that in particular these processes are updatable with respect to time, and everything in sight is monotonic with respect to time, so that's not going to be a problem. See, instance mo time, and I really don't want to go there right now. I do want to find what is mo time. Yes, okay. This is mo time. So, and this is where those my funny bind operator is coming from. Right, so we've just seen the implementation of the free instance of this with no clever trickery going on. All the updates are fully explicit and all of that kind of stuff. Now, this is the weaponized version that you program against, and it's deadly. Okay, so what is it to be a tiny monad? Well, it's to map predicate. It's a predicate transformer on conditions. So again, return says if your post condition already holds, you're done. And what does bind say? So you should read something like MGS as the assertion, I have a plan to achieve G starting at time S. That's the way to read this. Okay, so how do we get there? Suppose we have a plan to achieve F starting at time S. Okay, we might not get the F until sometime later, right? Okay, so this T is the later time when we actually get our hands on the F. So we're saying, okay, whenever that is, there will be a segment of progress that which gets us to T, and it comes from S. So this is us hypothetically, right? Here's how times arrive in practice. Right? This bind operator universally quantifies over a hypothetical time. And those are the times that matter. Not any actual concrete value of the type or of the kind time, but the hypothetical ones bound by this for all. So you can see this is going to introduce a new time. It's going to introduce a new segment that gets to that time from where we were. So if you want to see what's an example here, you can think of this. Oop. It's going to be fun. Maybe I should just hold on to it. All right. So, we're here. We do a bind. This is going to be our T. This is going to be our segment. And that goes in the instance context for this resumption. The other thing we get our hands on, the thing that gets bound by the lambda after this bind operator, you can see it's already Kripke. So that's to say we get a thing, but we don't just get the F at time T, we get an F that is good for any time after T. And it's Kripkeified already when we lambda abstract it. So if we go back to the program, you can see that's what's going on here. These are all, because they're coming out of they're being lambda abstracted in the continuation of a bind, they're already Kripkeified. They are good for any use time in the future, and we're going to be able to work our way back along the timeline, piecing together the segments to update them without lifting a finger, as Simon does it all for us. Oh, yeah, so that was that. And then the then version without binding is the same deal. It's just the one where we bind and throw away. Nothing to see there. So, okay, is this at least remotely plausible? I've got that's the sort of general picture, is that MoTime, this is the weaponized gadget that you want to program against, because it makes sure that everything you're working with is self-updating when it's handed to you. And this is also the thing which ensures that we get that the instance context is a linear sequence of segments that relate, these abstractly quantified times, which means that the kind of the instance search that we programmed earlier is just going to be able to haul its way back along the timeline and put the pieces together. So the apparent magic of that implementation of algorithm W is it's really a very carefully hidden behind the scenes peddling. I hope that's at least plausible. If anyone wants to run away, it's a good time to run away, because then we can, this is a pause and then dig the next layer down. But are we good? Okay. Because what I've given you here is a general notion of what MoTime is. I've given you how to turn that, and this is weaponized. Everything's as implicit as possible. But I gave you earlier a definition of the free monad where everything was fully explicit. There was no type class jiggery pokery, and what I could tell you now, but I'm not going to, is how to get between one and the other. That comes even later. I want to give an example of this an interface that we use this way, that is the interface that we're doing the type inference with. That's the thing called, I think I called it W. Yes, I did. Okay. So this is the interface. If you think about this, what I'm basically saying is, if you are the type inference process, what are the ways in which you're allowed to shout help? That's what this definition is giving. And you can see it's in predicate transformer style. So this is to say, at time I, what am I allowed to request? And then my requests are given by some post condition which is time indexed, and they might be satisfied sometime later. So what am I allowed to screen for? So in particular, I mean, maybe I should do these one at a time, but typical thing, for example, is this thing we saw earlier, vsca. What is the type scheme for this variable, right? I give a program variable, and what do I expect to be told? I expect to be told the type scheme of that variable. However, that type scheme is subject to the action of substitution, right? It contains unification variables. It might get updated. So I don't just want a type scheme. I want a time indexed type scheme that knows how to update itself. So that's what this dreadful portmanteau is. It's a scheme in time. And so that's a perfectly reasonable thing. Likewise, we know in the variable rule, we're going to say, we're just going to want to say, look, here is a type scheme that I know. I want you, with whatever magic you have available to you in the environment, to make me the right monotype instance of that type scheme for whatever I happen to be doing. So this is the thing when we're in the variable rule, we look up the type scheme of the variable, and then we know that the variable usage is supposed to stand for some monotype instance of that. So we just ask the world, tell me what's the right instance. And how the world deals with that is a whole other matter, right? So are we good with those two for the variable rule? Is this now making sense? It's a two-step process. Both steps are slightly magical. Right? But we first of all say, what's the type of X? And then we say, choose the right instance of that type scheme. We'll say, what's the type scheme of X? Choose the right instance of that. That's the type of X. Everybody fine? Right. Okay. So let's truck on. Next up is this guess thing. But if we look at guess, go find it. I'll translate this for you. Guess is implemented using instantiate. I'll translate. The type scheme that I'm instantiating is none other than for all alpha, alpha. That's what that thing which looks like. It's like I'm spitting out a plum stone or something. That's this, right? And if we instantiate this type scheme as a monotype, we will indeed guess our type, right? So that's guess. Okay. And then we need decal. Right, so what does decal do? Decal is in effect handler rather than effects. Our first example of an effect handler. We'll go and look at its implementation in a moment. But you say what variable, what program variable you care about, and what its type scheme is at the moment. And then that's going to handle various effects that show up in the course of inferring the type of the body of the lambda. Okay? So let's look at what decal does as a handler. Here we go. Okay? So let me just take the unhelpful highlighting off. What have we? Right? We're going to get the program variable, and then we're going to get something which works at all times that takes a type scheme and some process which has the W interface and computes a V, and we're going to give back a version of the same process with some of the effects handled. So we're listening out for stuff this process is doing in order to say how it's done. Okay, so boring stuff. If the process we're handling returns, great, we return. What we're actually listening out for, oddly enough, we are responsible for the declaration of X. So we are listening out for processes that say, what's the type scheme of X? Because that's what we're good at. We're good at, right? We're good at one thing, knowing the type scheme of X. So if we see a request that is calling, what's the type of Y, and Y is X, with resumption K, then we're like, me, I know this one, and that's great. I say, sure, I'm going to call you back I'm going to carry on handling because I still know the type of, that X has type scheme S. That hasn't gone away, still in scope, hasn't evaporated just because you've used it once. And I'm going to call the resumption, and I don't know anything new has happened, so I'm going to say no progress, and I'm going to tell you the answer. So that's me doing the thing I know how to do. And then if we fall through with any other command, then, well, I don't know how to do this one, but maybe my environment knows how to do this one. So what I do when I get a command that I'm not ready for is that I call that command myself. Somebody further out the stack is going to worry about this for me. And then they're eventually going to call me back with this resumption, and they're going to give me an update, and they're going to give me a result. And that update's interesting, because that update might tell me that my beloved S, the type scheme of X, has improved. So I'm going to carry on handling what is the type scheme of X requests, but S has been improved by the update. At which point, and in that scope, I'm going to invoke the continuation, passing it the update and the result that I was given. So this is me secretly updating on the fly the type I know X has, given the progress that's happened. This is where the actual wiring is being done of the information being approved in the handler. Okay? That's a little piece of fun. So now you can see what happens. This is what's going on. You know, back in the day, we guessed a type S, and we know what that type is because we've just instantiated this thing. That type is a fresh unification variable. At the time we declare X to have that type, it is a fresh unification variable. We know no better, but goodness knows what updates will happen during the course of infer B. And by the time we reach here, of course this S is Kripke, by the time you reach here, it will have been updated with whatever substitution happened during this process, and this will be exactly the right type to give back. Alrighty. The application case is actually remarkably boring under these circumstances, assuming that unification works. Actually, but it is a good time to look at unification. Let's look at unification, because that's also apparently completely bonkers. We're trying to unify two types. And what we start by saying, if they're already equal, don't bother. Which, you know, that helps a lot. Okay? Then we say, look, if they're both function types, then unify the source types, unify the target types. Hang on a minute. If you've done this before, you know instead of saying unify the source types, I should be saying unify the source types, get the substitution from that unifier, do that substitution to the two target types, and unify those. But am I saying that? No, life just got easier. Don't have to do that anymore. Right? These are my gnarly pattern synonyms that automatically Kripkeify the pieces. So S0, T0, S1, T1, they are Kripke. So this T0 and T1 does mean the target types after they've been updated by the substitutions resulting from unifying the source types. It just doesn't say that anywhere here. Isn't it? The entire talk is telling you what the program is not saying. It's just a massive magic trick, making the actual program disappear. But isn't that progress? Right, okay. And then the other thing that happens, fun stuff, is either way around, if we get an existential variable and a type, a unification variable, yeah, so x is density quantified, and a type, either way around, we can't do anything about that ourselves. This is the point at which we scream to the world, make this true! You know? Because somebody else, somewhere else, is responsible for managing that unification variable, not us. And they have the power, if anyone has, to make this equation true. So we're basically saying, oh, I found a variable, wake me up when this variable has the right value. So make is our next effect that we're going to look at. So back to oh, what's going on? Oh, left. Oh, I can't operate. Oh, no, don't do that. Right. So here's make. The return value of make is not interesting. It's really a command. We're just saying, make it so. We give a type. We give a unification variable, and we are hoping that by the time we're done, the unification variable is equal to the type, by hook or by crook. What this list is, we'll see in a minute. But let us now see what's going on. We also saw in the lambda case, we saw decl to declare something with the type scheme. Oh, that was the thing that responds to requests. Something else is involving make. So what's the handler for make? Oh, it's called guessing. We haven't, this shows up inside other stuff. But guessing is a handler that manages make. So what happens? Guessing takes a unification variable, an existential variable, and I'm the handler responsible for guessing the value of this variable. So you should think of this first input as me, and then we're handling a process which may or may not have opinions about me. So what happens? The business happens when we're guessing existential variable E, and along comes a make request, which is trying to make some other thing x equal to t with resumption k. So we care about the answers to two questions very deeply. First of all, is it me? Is the variable that someone is wanting to define actually my variable? So that's this first condition here, E equals x. The other thing we need to know is, does the type that someone wants to make x talk about me? So either x is me or t, is x me? Does t talk about me? If either of those is true, things are interesting. So let's first of all look at what happens if they're not interesting. Right? If this problem is literally nothing to do with me, then I forward the command, I wait for the response, I reinstall myself, none the wiser, still guessing me, and I call the continuation. So this is, nothing happened here. We learned nothing about me. I'm still here. I'm still a process looking after this one unification variable. Okay. If both of these things are true, right? If the type that we're trying to instantiate is me, and the type that is, but the type that we want me to be also talks about me, then we've got an occur check failure. At which point we issue instead the barf command because we're rejecting this whole situation, right? It's impossible. Okay. Otherwise, there are two possibilities. I'll do the second one first. So the variable to be instantiated is not me, but the type it's defined to be involves me. And what that means is that I'm in the stack of processes too late to be of use, right? We're working our way outwards through the context, looking for X, trying to make, and I know that X is more global than me. If X has any chance of becoming T, I have to move to be in scope for X. So that's what this list is. List is the list of variables whose scopes have to be extruded in order to make the definition possible. So what happens? I carry on making a call, attaching myself to the list of variables to be extruded. And I make the same definition with the same continuation. And you'll notice here, I'm not re-invoking myself handling the continuation. I've bundled myself into the list of things to be extruded. Okay, there better be a happy ending. I've just been put in the car boot. Okay, so here's the happy ending. This is the bit where, yes, the variable being defined is me, and what's more, my definition doesn't talk about me, so that works. Now, what happens? First of all, I have to rewrap what happens next in guessing handlers for all of the dependencies that are being extruded. So this is where the list of extruded variables turns back into a composition of guessing handlers at, further out in the stack. And then we carry on by calling the continuation of make, but with some non-trivial progress, namely that we should be substituting t for x. So this is where something actually happens. It's that the continuation gets told, we're no longer trying to guess what x is, so that there's no rewrapping. We're no longer doing a guessing handler for x because we know what x is. That has turned into the update that we send to the continuation. Substitute t for x, folks. And x is gone now from the problem. Okay? That's real stuff happening. Okay. But there is another subtlety which we'll come back to. You'll notice, and this is significant, that this handler is fussy about what the process it's handling is up to. We've seen other handlers which say, I don't care what this process is trying to do, I'm talking about something in the middle. This handler also has opinions about the end game. The process that we're handling has to be trying to compute a type scheme. And we're also trying to compute a type scheme. And that's important. We'll come back to that in a minute. But I'm trying to do these things in story order, not code order. Okay. So actually, we should now get interested in what this thing does, right? We said what the command was supposed to be, like magically, cheerio, magically instantiate this type scheme to a type. What the hell actually handles that? Let's go looking. Oh, why am I? Right. So this is a thing called block. And it manages a block of unification variables. And it handles instantiation requests. It's like saying, so you should think of block as sitting there in the context saying, I am somewhere you can put unification variables, and if you ask me for one, I'll give you a unification variable. So what happens is we're waiting to receive requests to instantiate a polymorphic type as a monotype. Actually, I should start with the end. Here, what happens? Sorry, this is the monotype. We arrive at a monotype T. So there are no universal variables that we need to invent values for. So we're just saying, okay, we've reached the monotype. We're just going to call the continuation with the monotype. Job done. However, it's possible that we're instantiating a polytype. That's what this P says. It's polymorphic with body S. So what do I have to do? I have to invent a fresh type variable, and then I have to start guessing what that is. So what happens is that a guessing handler goes outside the reinvoked block handler. And then we carry on instantiate. We instantiate the first quantifier, and then we keep going. So that's basically saying the block handler is sitting there. Anytime it gets an instantiate request, it installs guessing handlers just behind it. So it's like the mother duck with the ducklings of the guessing handlers behind it. And anytime it's asked to instantiate a polytype, another little duck appears. And we carry on going. We will see anything else gets forwarded. Something's going on with the return. Not ready for that story just yet. Okay? So that's the block handler is handling instantiate. Where do block handlers come from? Well, where do polytypes come from? They come from lets. So this, when we get a let in Hindley-Milner, we install a block that is willing to deal with polymorphic things. Cool. And we sit here just being ready to deal with all the polymorphism that happens in the inferring of D. Okay? Now we need to pay attention to the types. Right? So you'll notice that block is agitated. It deals only with types that give back a monotype, a timed monotype, but it returns instead a process that computes a type scheme. So the magic that you're missing, that is the big complicated bit in Milner's rules, is about to happen, except it's not going to be magic. What happens when we get our returned type, we pass on a type scheme that happens to be a monotype. And remember, we've got our little ducklings of guessing processes just behind us, and we're now feeding them a type scheme that happens to be a monotype. And that's where our type scheme comes from. So when I get a return, I say, oh, goodness me, here's a type scheme. And in the course of finding that type scheme, nobody solved me. That means I should be generalized over that type scheme. So this is the point where the universal quantifications go in. The guessing processes for unification variables that don't get taken up on the offer generalize the polymorphic type schemes, and they're sitting in the right place to do so because all of the scope extrusion has happened properly. There's sort of no mad dash to figure out what depends on what. We did that really carefully with the scope extrusion when we were, well, you know, right here. All of that. That's managing the whole of the generalization process by just trying to keep things topologically sorted. So that's the story of Hindley-Milner implemented in an effects and handlers style, where we're using essentially Kripke semantics to talk about possible future worlds, which we enter by actually learning some stuff, and this whole magical business of persuading the type class system to figure out what the hell has happened in the meantime, which allows us to write suspiciously simple programs that do what they obviously should. So I think that's progress. And I've rather cunningly run out of time before I have to say how the trick is done. So I'm going to stop there. So pop the pointer down.
Is there anything intrinsic about information having to increase with a setup? Or I guess it depends on how increase is defined. Right?
Yeah.
Could something go out of scope or be consumed?
I mean, those events are tricky. You need to, if we're trying to work in this situation, then we need to, the Kripkeification is only justified by saying, well, whatever increases, whatever we have now, we've still got it in some form. You also have to be extremely careful to ensure what I call the PF property of processes, the sort of je ne regrette rien. That's to say, any decision that a process makes on the basis of limited information ought to be one it would make again, even if it knew more. That's to say, you have to be open to all possible information increases, which does not mean everything's completely monotonic. There's an only just kind of situation where if you can detect that there is no way information can possibly increase, then so that's an example actually. This thing here, right? This is us saying, look, nobody is ever going to guess E now because this is the thing, because E is about to go out of scope. So I'm never going to regret this generalization step because nobody is going to tell me, hang on a minute, E was something in particular. This is the point at which I can do that, where I can say, I know there's no possible future information increase, so I'm all right to commit. But yeah, you absolutely need that respect for, and so you can cook whatever notion of progress you're willing to respect. You know, there's nothing that says it's about substitutions or it's about something in particular. And indeed, this trick is played by other people in other situations. Sam Staton has a version of this story which is talking about heap allocation. So if you've got malloc but not free, you can create new references. Then you're in a situation where your programs, which talk about only the old references that were around at the time, make perfect sense if a few more references have been allocated. So all you're doing is tracking heap inclusion, which is completely fine. But yeah, free is then harder, right? You then need to know that nobody's ever going to talk about that again, which is a reasonable thing to want for free, right? The way to, it's exactly, if you're going to go backwards, you have to watch scope. is the message. And that's the thing we do, even a little bit here.
One more quick question before we